Hello students, welcome back to the lecture 34 of this course. In this lecture I will discuss about mass spectroscopy. Mass spectrometry uses high energy electron to break a molecule into fragments, and when you break a molecule into fragment and you analyze the fragments, it can provide information about molecular weight and the structure. The impact of a stream of high energy electrons causes the molecule to lose an electron, forming a radical cation. So, when high energy electrons is bombarded on molecule lose an electron and forms a radical cation. Radical cation is a species with a positive charge and one unpaired electron. So, here is an example of CH4 molecule getting bombarded with electron. So, this electron takes out one more electron and generates a radical cation whose molecular weight is 16, or M by Z ratio is 16, and you get a peak at 16 corresponding to this radical cation. The high energy electron can not only remove electron, it can also break molecule or the radical cation into fragments. So, suppose if you bombard ethane with electron, molecular ion with M by Z ratio is equal to 30 will be formed. Apart from that, this radical cation can lose a hydrogen radical, and a species with molecular weight 29, M by Z ratio 29 will also be formed. The radicals are not detected in mass spectroscopy. This molecule can also break into CH3 cation and CH3 radical. The radical is again not detected by mass spectrometry, but this positive ion will be detected and a peak will be observed at 15. Now, there are certain terms which we should be familiar if we are dealing with mass spectrometer. One is your molecular ion or parent ion peak. So, this basically corresponds to radical cation having mass of original molecule. For example, if methane is bombarded with electron, one electron is removed and the left one is your molecular ion. Similarly, in case of ethane, this is your radical cation, which is basically your molecular ion. Molecular ion is usually the highest mass in the spectrum. Exceptions are when there are isotopes of higher molecular weight is present, and in some cases molecular ion peaks are absent. So, this is your mass spectrum of ethanol, which has molecular weight of 46. So, now you can see that M plus ion peak is here, M plus ion peak is here, and you can get a peak at M minus 1. So, the cations that are formed are separated by magnetic deflection. So, what happens that these molecules are bombarded with electron beam here, and then ions are produced. This ion beam gets deflected here in the magnet. The ions that are too heavy bend too little, whereas ions that are too light bend too much, and then only ions of right mass can enter the detector. Once it enters the detector, the peak is recorded. The peak corresponding to that ion is recorded. So, in mass spectrometer only cations are detected, radicals are invisible in mass spectrometer. and the amount of deflection observed depend on mass to charge ratio, m by z ratio. Most cation formed has a charge of +1. So, the amount of deflection observed is usually dependent on the mass of the ion, usually dependent on the mass of the ion. The resulting mass spectrum is a graph of mass of each cation versus its relative abundance. So, basically you are plotting relative abundance versus your mass of each cation. The peaks are assigned as an abundance as a percentage of base peak. So, base peak is considered to be of 100%, and then abundance is assigned for each peak, which is basically expressed as a percentage of the base peak. Base peak is not the same as molecular ion peak. Base peak is the most intense peak in the spectrum. So, base peak is not necessarily the same as parent ion peak. So, now again let us go back to mass spectrum of ethanol. Here you can see that this is the molecular ion peak, which corresponds to molecular weight of ethanol, and it comes at 46 m by z ratio, but this is less intense in comparison to this peak. This peak is most intense one and hence called base peak, whereas this one is molecular ion peak. And then you assign abundance with respect to this base peak, and here you can see this has been assigned 100. So, this is your relative intensity, and other peaks are assigned a relative intensity as a percentage of base peak. Most elements occur naturally as mixture of isotopes. So, the presence of significant amounts of heavier isotopes lead to smaller peaks that have masses that are higher than the parent ion peak. For example, you can also see a peak with m by z ratio m plus 1. So, a peak that is 1 mass unit higher than m plus. You can also see a peak that is 2 mass units higher than m plus. Now, there are certain very recognized elements in mass spectrometer which can give you an idea about what kind of structure that molecule has. For example, if there is odd number of nitrogen, then you will observe a odd molecular weight peak. So, in this case you can see there is only one nitrogen, and you can see a molecular ion peak which is equal to 41, which is an odd number. So, odd number of molecular ion peak will basically show you that the molecule may have odd number of nitrogen. This is a very important element in mass spectrometer, that if suppose your molecule has bromine, then its m plus and m plus 2 peak will be of equal intensity. M plus and m plus 2 peak will be of equal intensity, and presence of equal intensity m plus and m plus 2 peak will suggest that molecule has bromine atom. Similarly, if molecule has chlorine atom, then m plus 2 is 1 by 3rd as large as m plus ion. So, m plus 2 you can see here, m plus 2 is 1 by 3rd of m plus ion, and that can tell you that a chloro group is present in the molecule. If the molecule has a sulfur atom, then you can see m plus 2 larger than usual. It is almost 4% of m plus ion. So, here you see that M plus and this is M plus 2 peak, and M plus 2 peak is a 4% of M plus peak. So, M plus 2 peak is generally larger than usual, larger in comparison to whatever you have observed, and that is almost 4% of M plus peak. If a molecule has iodine, then you can see a peak at 127, M by Z ratio 127, and you can see it here that this molecule ICH2CN has one peak at 127. That suggests that your molecule has probably iodine, and then you will also observe a large gap between M plus and the next peak, M plus and the next higher molecular peak. So, if there is a large gap, it means I is getting detached from the molecule, and the rest of the molecule, which is as cation form, has lower molecular weight. So, this is about looking at the different kind of peak and getting information about particle element. For example, the presence of chloro group, bromo group, iodo group can be estimated from looking at the different peaks. For example, M plus 1 peak, M plus 2 peak. But we can also look at the fragmentation pattern to know the structure of the molecule. So, when a beam of high energy electrons is bombarded on the molecule may break into fragments. One fragment will exist as a cation, whereas another fragment will exist as a radical. So, bonds break to give most stable cation. So, generally if there is a breaking of the bond, then most stable cation is formed. Stability of radical is less important. So, if you look at alkanes, mass spectrum of an alkane, the fragmentation often splits off simple alkyl group. For example, there can be loss of methyl group, loss of ethyl group, loss of propyl group, and loss of butyl group. And so, the peaks will be obtained at the molecular weight minus 15, the mass of M plus ion minus 29, mass of M plus minus 43, mass of M plus minus 57. So, the peaks which will be obtained will be 15 unit smaller than molecular weight, 29 unit smaller than molecular weight, 43 unit smaller than molecular weight, and 57 unit smaller than molecular weight. Branched alkanes tend to fragment, forming the most stable carbocation. Now, look at the fragmentation pattern of 2-methyl pentane. So, M plus is obtained at 86. So, 86 is its molecular weight. Now, if it loses a methyl group, then you will get a peak at M minus 15. If it loses CH2, CH3, then 15 plus 14 is 29. So, this peak can be assigned to M minus 29, and if it loses this CH3, CH3, then so you see this is 12 into 3, this is 36 plus 3 plus 3 plus 1, 7, 43. So, if this molecule fragment giving this cation this cation plus CH2, CH2, CH3 radical, you will get a peak at M at 43, peak at 43, whereas if you get this CH3 plus radical plus CH2 plus CH2 CH3. So, in this case you have your 36 plus 7 43, this is also 43. So, so in both case you will get a peak at m minus 43, and this is basically equal to 43, this is basically equal to 43. This is the fragmentation pattern for alkenes. The fragmentation generally forms resonance stabilized allylic carbocation. So, if you look at this case, allylic position is this one. So, the bond breakage will happen at this position, the fragmentation will take place at this position, giving you this cation. Since this is resonance stabilized, so this will be formed in greater amount, and so this molecule, this species will correspond to the base peak. This molecule will correspond to a base peak. Size of this species is 55. So, you are seeing a most prominent peak at the position 55, and that is basically a base peak. Similarly, in aromatics, the fragmentation can take place at benzylic carbon. Fragmentation will take place at benzylic carbon, forming a resonance stabilized benzylic carbocation. So, you can see this is your benzylic position, and the fragmentation will take place at this position. So, that a benzylic carbocation is formed, and that can go to tropylium carbocation, and this has a molecular weight of 91, and so most of the aromatic compound will give a peak corresponding to 91 if there is CH2 group attached, and that is basically because of benzylic carbon, and this is the percentage of this will be more because here plus is resonance stabilized, and so this will be as a base peak. Aromatics may also have peak at m by z is equal to 77 for the benzene ring. So, suppose your nitro compound is there, this is nitrobenzene. So, breaking will take place at this position, and you expect a peak at 77. So, if there is no CH3 group attached to benzene, then this will be a base peak. This will be a base peak. Now, if you go to alcohols, fragments can easily result into very small or missing parent ion peak. You may not see parent ion peak or very small ion peak. You can get M plus minus 17 because of loss of hydroxyl radical, or you can see M plus minus 18 peak, which is because of loss of H2O. Commonly, it loses an alkyl group attached to carbinol carbon, forming an oxonium ion, and 1 degree alcohol usually have prominent peak at M by Z is equal to 31, corresponding to CH2 double bond OH plus. This is mass spectrum of 1 propanol, and it can break here, giving you CH2 plus OH, and here your plus charge is resonance stabilized, and so it will act as a base peak with maximum intensity. Apart from that, you can get M plus minus 18 peak, which is because of loss of water molecule, and then M plus peak is very small. M plus peak is very small in case of alcohols. For amines, if there is odd number of nitrogen, and then you will get M plus peak which is odd. Again here alpha cleavage will dominate, since alpha cleavage gives you iminium ion and in which plus charge is resonance stabilized. So, take this case of an amine, the break will take place at this position, and so that your plus charge will be here and this will be resonance stabilized. So, plus charge will come here and then this will get resonance stabilized, and you will get iminium ion at M by Z value of 72, M by Z value of 72. Now, look at the fragmentation pattern. So, if there is a breakage here, then you will get a peak at 72. There is another cleavage possible at the alpha, again alpha position. Here you see if it breaks at this position, then again this plus charge will be resonance stabilized and this whole mass will correspond to 86. This whole mass will correspond to 86, and thus if you are you go for mass spectrum this, you will see a peak at M plus, you will see a peak at 86 and you will see a peak at 72. Now, let us look at ethers. Again here alpha cleavage will be more predominant, since alpha cleavage will give you a positive charge which is your resonance stabilized with the lone pair on the oxygen. So, if it breaks here, then there will be plus charge here and this will be resonance stabilized and you will get this ion. Loss of alkyl forming oxonium ion, and so if there is a loss here, then O plus there will be plus here and then there will be loss of one H here and you will get this oxonium ion. Loss of alkyl group can also happen where your plus charge is on alkyl group, plus charge is on alkyl group, and that is how a carbocation can get formed. Now, let us look at the fragmentation pattern of diethyl ether, and this is mass spectrum of diethyl ether. So, a peak will be formed at M plus, this is the molecular ion peak, and this corresponds to your 74, this corresponds to 74, and if suppose there is a loss of this CH3, am I right, loss of this CH3 means 74 minus 15 and that will be 59, and so you get a peak at 59. So, this is because of alpha cleavage and plus charge is on CH2 plus, which will be resonance stabilized due to lone pair on oxygen. The next one will be because of loss of this one CH3 CH2 means you are removing 29. So, 74 minus 29 is 45. So, basically you have CH3 CH2 and O plus, okay, CH3 CH2 O plus, and so you will get a peak at 45, and then you can also get CH2 OH, and that will there will be a peak at 31, there will be a peak at 31. Now, let us look at the fragmentation pattern of the aldehyde. The fragmentation may form acylium ion. So, H radical will be removed giving you acylium ion. So, if you take RCOH, the breakage can happen here giving you RCO plus which will be resonance stabilized, So, common fragments are m plus minus 1 for this, and then you can also get fragment due to breakage here. So, R plus HCO radical. So, R plus will give you peak at your m plus minus 29, because this corresponds to 12 plus 16, 28, 1, 29. So, this corresponds to 29. This corresponds to 29 and this corresponds to m minus 29. Now, let us look at the fragmentation pattern in hydrocinnamaldehyde, and this is the formula of hydrocinnamaldehyde. So, you will get peak at 134, which is your molecular ion peak. Hydrogen can be lost, and that is how you can get a peak at 133. Then if there is a loss of this COH group, then you get 105, because this corresponds to m minus 29, and if you take minus 29, then this comes out to be 105. Then if there is a break here, then you will get a peak at 91, you will get a peak at 91, and then your peak at 77 can be observed because of this phenyl ring. Ketones fragment leads to formation of acylium ion. So, you can get this or you can get this one. So, two different kind of fragmentation is possible, and that is what you expect in the mass spectrum of your ketone. Here is mass spectrum of 2-pentanone. Here is the mass spectrum of 2-pentanone, and this is the formula for 2-pentanone. This is formula for 2-pentanone, CH3, CH2, CH2, CO, CH3, and there can be fragment formed from this fragmentation leading to CH3 CO plus group plus CH2 CH2 CH3 radical, and when this results, then you have mass at your 43. So, this corresponds to 15 plus 12 plus 16, and this is 853 and your 43, right, this is 43. So, you will get a peak at 43, then there will be peak at this position. So, if this CH3 breaks out, then you have CH3, CH2, CH2, CO plus, and this is 15 plus 14 plus 14 plus 12 plus 16, and this is 29 plus 26 plus 16, and 6, 6, 12, 9, 1, 21, 2, 8, 1, 3, 2, 5, 2, 7. So, peak at 71. So, you see here peak at 71 is formed, and this is your molecular ion peak. Ketone fragments will be formed when ketone breaks from two sides of CO group, So, if it breaks here, then there will be your peak at 43, whereas if there is a break here, then you will get mass peak around 71. Now, look at the fragmentation pattern of ester. Common fragment of ester includes a fragment resulting from loss of OR dash group, and so a peak is expected to be observed at the molecular mass minus OR dash, mass of OR dash group. Another fragment which can result from ester is due to loss of R dash group, and in that case the observed peak will be at the molecular mass minus mass of R dash group. And here is one example of fragmentation pattern resulting from an ester. So, if the CH3O, there is CH3O groups leaves giving cation having C6H5CO plus structure, that will give you peak at 105 and molecular mass peak will be at 136. So, 136 minus 15 is 121 and this is minus 16. So, 15 is due to CH3 and there is a loss of oxygen also. So, this is 105. So, you will see a peak at 105 and that will be a base peak. Another peak may result from the loss of this whole thing, this whole group, and that will be because of this ring, and that is expected to be at 77. This is expected to be at 77. Now, there is another thing which you keep in mind. This will help you in deriving the molecular formula that is known as rule of 13. That is known as rule of 13. The rule of 13 can be used to identify possible molecular formulas for an unknown hydrocarbon. For example, if you have CnHm, N corresponds to the subscript with carbon and M, well, the subscript of hydrogen. It means there are N carbon in the molecule and there are M hydrogen in the molecule. So, first thing is that you divide the molecular mass of the hydrocarbon by 13 and that is why this is known as rule of 13. It will give you integer and the remainder we are going to utilize in step 2. So, N is simply M plus divided by 13 and M is N plus remainder from step 1. So, whatever remainder you got in the step 1, just add to N value and that will give you the M value. For example, suppose I have a hydrocarbon with formula with molecular mass 106 and that is what you get from suppose mass spectrum. Now, you want to know that what will be the formula of hydrocarbon, and what we need to do is you take 106 and divide by 13 and that is going to give you the integer 8 and the remainder will be 2. Integer 8 and remainder will be 2 and so this is basically like, so 8 2 by 13 is equal to 106 by 13. So, this will give you the value of N and M will be N plus remainder. So, remainder is 2. So, 8 plus 2 10. So, this is your the formula for hydrocarbon will be C8H10, C8H10, C8H10. And once you know that, then you can know how many unsaturation is there and that can give you an idea of the structure of the molecular species. Now, suppose a heteroatom is also present in the hydrocarbon. For example, in alcohol oxygen is there, in amine nitrogen is there. Then what you need to do is subtract the mass of each heteroatom from the molecular weight. So, if you expect that there is one oxygen atom, then you simply subtract the mass of each heteroatom. Okay. Then calculate the formula for the corresponding hydrocarbon, add the heteroatoms to the formula, add the heteroatoms to the formula. From that you can know what is the formula of the compound. So, once you applied rule of 13, you know the formula. Now, next step is to get the degree of unsaturation, and degree of unsaturation is given by this equation: 2 into carbon, C is basically number of carbon, 2 into number of carbon plus 2 plus number of nitrogen, which is given by N, minus number of halogens, which may be either fluoro group or chloro group or bromo group or iodo group, and then you subtract that with the number of hydrogens and then divide by 2, that will give you degree of unsaturation. So, just by looking at molecular mass you can know the formula, and once you know the formula you can calculate degree of unsaturation, Okay, so let us see and see whether we can predict the formula from the mass. So, if you know, suppose that your molecule has carbon, hydrogen and oxygen, carbon, hydrogen or maybe oxygen, then if you have a M plus is equal to 86, then your formula can be C6H14, C5H10O, C4H6O2 or C3H2O3, and this you can get from, so suppose 86 divided by your 13 and that will give you 6. So, 13 into 6 is 78 plus 8 by 13. So, formula will be C6 and H 6 plus 8 14. Now, there is possibility that one oxygen can also be present. In that case, you will write 86 minus 16 is equal to 70 divided by 13, and that will give you 5 by 13, 5 by 13. And so, your formula will be C5 and 5 plus 5 10. So, H10 and 1 oxygen. If suppose you expect that there is a 2 oxygen, then you have a 86 minus 32, it means you have 4 and 5 54, and then you divide by 13 and then you will get 4 2 by 13, and so C number of C will be 4 and number of H will be 4 plus 2 6 and then O2, and similarly you can get this formula. So, these are the formula which you can guess just from the molecular weight. And if M plus is 156, then you have this many possibilities, And if suppose we have hexane, so here you see this is hexane. So, suppose what we are getting is, if we have a hexane, then what do we expect, that there will be peak corresponding to M plus equal to 86, and then the first loss of methyl group will result into loss of mass by 15, and that then you will get 71 M by Z value. The second loss of CH2 CH3 will result into loss of CH2 CH3, which is 29, and if you subtract 86 by 29, then you will get 57, and 57 minus 14 is 43, and 43 minus 14 is 29. So, these peaks you expect, and here you see that you have got peak at 86, you have got a peak at 57, you have got peak at 43, and you have got a peak at 29. And if you get this spectrum, then you are sure that you have a hexane, And so, by combining your M plus information plus from M plus peak and looking at the spectrum, you can know what structure you have got. Now, we can also distinguish between two different your isomer. For example, methyl cyclohexane or ethyl cyclopentane, both have same molecular weight, 98, 98. So, they cannot be distinguished by M plus ion peak, but its fragmentation pattern is going to be different, and that is how you can differentiate between these two molecules. Suppose you have sample A and you want to know whether this sample A is basically this compound or this compound, and this is a spectrum of sample A, and then you look at this peak. There are these 3 peaks and they are very characteristic. This is M plus peak which is equal to 98. So, this is molecular weight of 98, and then if there is a loss of CH3, then you can get a peak at your 83, peak at 83, that is what you see. This is because of loss of CH3, and if there is loss of CH3 CH2 group, then there will be loss of 29, and so 98 minus 69 gives you a loss of 29. That is a base peak, and that can only be possible from this compound, only can be possible from this compound, because this the loss of CH3 CH2 is more prominent in this compound, and so base peak at 69 is due to this compound. And now look at the sample B. How does the fragmentation pattern of this looks like? Here M plus is equal to 98, and now here the base peak will be due to loss of CH3, due to loss of CH3, and that is why you are seeing a big peak here. And so, just by looking at the structure, you expect the base peak in this due to loss of ethyl group, whereas base peak in this due to loss of methyl group. And so, just looking at their mass spectrum, you can distinguish between these two compounds, So, I will stop here. I suppose that I have given enough clue to you how to use mass spectroscopy, for the structure determination of organic compound. And this is my last lecture. So, I believe that I have given a very good flavor for you of different kind of spectroscopy. I have started with the theory part, and I have tried to go into lot of application corresponding to each spectroscopy. We not only looked at the spectroscopy, we also have looked into microscopy, and if you understand the principle, it is not very difficult to use spectroscopy for structure elucidation and other kind of application. Application is not only for the elucidation of a structure. The application of spectroscopy include your analysis, include your qualitative determination, include quantitative determination, include your applications in environment, application in forensic science, application in pharmaceuticals, biopharmaceuticals, application in your cosmology. So, there are a lot of application, and your potential of spectroscopy and microscopy is vast, and so it is very difficult to give you all different kind of application which can be done using a spectroscopy, but I have given a good flavor of each of the topic, and so I believe that you must have enjoyed this course. Thank you very much.